Hello friends. In today's class we are going to talk about some methods related with deadlock detections. So welcome here and detection. Okay, so that is one method that do nothing to prevent the deadlock. It allows the system, let the system enter into a deadlock state, and once the system enter into the deadlock state, then it detect that by using some algorithm and then apply some recovery scheme. Okay, so Unix system basically has built in this way only, that let it be go into the deadlock, and after that we are going to see whether we can recover. We'll detect it and then finally we'll recover it. So if you have a single instance of each resource type, we have already seen that we can detect cycle. We'll maintain another graph that is called wait for graph. Okay, wait for graph, and wait for graph is something like pi to pj, where pi is waiting for pj resource. Okay, where pi is waiting for pj resource. Okay, so something like this, that if pi is this is a resource and this is its claim age, and this is allocated age to p2, then let's say pi and let's say pj, then in that case pi will be have age to pj. That means it is waiting for this process to free the resource. Now what it does is periodically invoke the algorithm and searches for the cycle in the graph. If there exists a cycle, then there exists a deadlock. Periodically invokes an algorithm that searches for the cycles. Okay, and if the graph there is a cycle, then there exists a deadlock. The simple method and a single resource, we have already seen that resource allocation graph consists of cycles. Also is the deadlock state. Okay. So algorithm detects a cycle in the graph which requires an order of n square operation, where n is the number of vertices in the graph. Okay, so we can do this entire thing in n square time. This is an example of resource allocation and graph. This is a resource allocation graph, and this is an equivalent wait for graph. Okay, so P1 is looking for R1. R1 is allocated to P2. So P1 to P2 there is an edge. P2 is looking for R4, and R4 is allocated to P3. To P2 to P3 there is an edge. P3 is looking for R5, and that is allocated to R4, then there is an edge. Okay, and both are looking. P2 is also looking for a resource R5 which is allocated, so P2 to P4 there is an edge. P4 is looking for R2 which is allocated to P1, so P4 to P1 there is an edge. Just remember that there is a two process looking for the resource R5 and which is allocated to P4. So both are waiting for this P4. Okay. Now you can see here that there is a loop in the graph, and loop in the graph signify what? Loop in the graph means that this system is in deadlock. Okay, detection algorithm is having its uses. When and how often it invokes depends on that how often a deadlock likely to occur based on the history, and how many processes will need to be rolled back. Okay. So how often is based on this the answer of this question, that how often a deadlock likely to occur and how many processes need to be rolled back. If detection algorithm is invoked arbitrarily, then there may be many cycles. There may be many cycles in the resource graph, and so it would not be able to tell which deadlock process caused the cycles. Okay, so arbitrarily you cannot execute. In that case, yes, we can detect the cycle, but we cannot say that only this is having the cycle. Recovery from the deadlock is about process termination, and about all the deadlock process, about one process at a time until the deadlock cycle is eliminated. And that is the good idea actually, to about one process at a time. In which order we choose to about priority of the process, how long the process has computed, and how longer the completion, resources the resource the process has used, resource the process needs to complete, and how many processes will need to be terminated, and if the process is interactive or bad. So these are some decision making criteria, you can say. So recovery from the deadlock is resource preemption, that we will select a victim and we'll select a victim which minimizes the cost. Let's say it has spent less time in computation, and then return to a safe state and restart that particular process. Okay, so we'll roll back. We'll just discard whatever computation it has done. The third point here in this case is the starvation. If the same process has been selected again and again, then we picked as victim, and then it will be that process might not get the resource properly. So that's all for this discussion. Thank you.